Well, we seem to have some glare there. Maybe that's a little better. I hope so. Ashley's with us. Good. Excellent. Monday, November 2nd. Why is this sort of crooked? Maybe that's a little better. Maybe I need to move this. Move that over a little bit. Not too bad. Okay, well, Ashley's with us, and let's see who else we've got here. Just Ashley, it's just you and me. Class starts in about 3 minutes. Do you have any questions?
Not at the moment.
That's fine. That's fine. Okay, well, let's see. What are we going to talk about today? Let me think here. What is the topic? This is November. I guess Newton's second law. It says here November 2nd, chapter 17, Newton's second law. Okay. That sounds good. There's some homework as usual. The homework is chapter 17, review problem 3. I could write that on the board. The homework is homework number 22, chapter 17, review problem 3. Okay. And the topic is Newton's second law for rotation. Hey, looky here. We've got Stuart, Ryan, Braxton, and Ashley. We've got a good class already. Good deal. Class is about to start. Did any of you have a question for me? Here's your chance. Nobody's saying anything. Well, maybe we could have a couple of minutes of review. That probably wouldn't hurt. Let's do that. One of the things that's important is finding the centroids. Let's talk about that for just a minute, and then we'll get into our fun topic here. Centroids. Did you know there's 5 different kinds maybe 6, at least 5. There's a center of gravity, center of mass, center of area, center of volume, center of length. How's that? 5? 5 different ones. Their formulas all look the same. Like they go like this. Or this would be the weight. And this would be the sum of all the weights. Now, that's just written in a in kind of a generalized direction. See, if you were to write the x component, it would go like this. If you were to write the y component, it would go like this. And you can visualize what the z component would look like. I won't bore you. Now that's the center of gravity. The center of gravity, where this is the weight. Now, what I mean by the weight, that's your mass times gravity. Now, unless you're in outer space someplace, if you're in an area close to the Earth's surface, gravity is considered to be a constant. It's really not. Did you know that if you're in the vicinity of a mountain and you're over here, did you know that gravity doesn't go straight down? It kind of veers off a little bit in the direction of the mountain. That kind of makes sense. So see, this is really a vector, and gravity has direction. Not only that, but it has magnitude. See, if you're in a place that has a big oil deposit underneath the surface, did you know that gravity is the acceleration of gravity is actually smaller if you're right over an oil field like that? Not much, but it's detectable. They use that for discovering oil. Anyway, there's the center of gravity. Now, the center of mass, if these weights can be written as GDM, come on now, GDM, there you go, where you take a small amount of mass, and this could be written as GDM. If the gravities are all constant, then you could pull the gravities out of these integrals, and they're constant in direction and magnitude, and the gravities would cancel, and you would have a center of mass. See, the formula for the center of mass goes like this. See, the gravities no longer play a role because they're all constants and they all cancel out. So there's the formula for the center of mass. And here, the formula for the center of mass in the x direction would be x dm over dm. And in the y direction and the z direction, same boring thing. And then there's a centroid of area. And the way it would look is like this. But instead of dealing with, I'm getting confused here. Where's my vector go? Well, it would really be the R, wouldn't it? What about these R's? I think I need my R there. Yeah, okay. Don't forget to divide by your total area, and your x centroid of area would equal to your x dA over the total area. And also you could get your y bar and your z bar over there. There's also a centroid of volume. I'm getting kind of bored of this and we need to move on. But you need to know that there's really 5 of those. See, the centroid of volume, the way it goes is R dV over dV, and this is really a vector. I forgot my vector sign there. And then you'll have a centroid of volume equals to x dV over dV, and etc. We could do a quick example, I guess, and then move on. Okay, we're going to do an example now. I didn't get to centroid of length, but you can do those too. In fact, right here, we'll do an example with the centroid of length. But did you know that? Did you know that there's 5 different kinds of centroids? And the kind that we use is this center of mass in this class here. That's your homework. You don't need me to write that. It's in the syllabus, or it's on Blackboard. But here's an example. Suppose you had a bent rod like this, and this bent rod has a fixed pivot. There you go. We need some distances here. I don't know. But this could be maybe, what's it look like to you guys? Here, I'll measure it. It is about 10 centimeters. 10 centimeters. 10 centimeters. We'll assume it's of uniform mass per length. What would be the centroid of length for that bent rod? We'll assume this is a 90-degree angle here. Well, you could put your axis right here. There could be y-axis and your x-axis here. Can you see that the center of this rod's right there and the center of that rod's right there? Yeah, pretty much. So, if you wanted the x component of the center of mass, it would be 5 centimeters times the length, which is 10 centimeters. Plus, well, that one is at 10 centimeters times the length, which is 10 centimeters. And you divide by the total length, which is 10 centimeters plus 10 centimeters. We'll see if this works. If you solve that, what do you get? I'm going to ask one of you outstanding students to plug that in and find the centroid, the x component of the centroid of of length. This is a centroid of length. Go ahead. I'm going to do it. You do it. Let's see what we get. Let me call on one of my excellent students here. Let's see. I'm always picking on Shane. Shane, unmute and say hello, please, Shane. He's not answering. Hey, Ryan, unmute and say hello, please, Ryan.
Hello.
Hello. Hey, Ryan, what'd you get when you plugged this in?
7.5 centimeters.
That's what I got. Now let's do the y component. The y component of the center of length. Well, it looks like it goes down. This is 0. Let's see if y is this way. This didn't go down at all. So it's 0 times 10 centimeters. But then you go down 5 centimeters times 10 centimeters. And you divide by 20 centimeters. And I get what's 50 divided by 20? 2.5. I get 2.5. Do you guys get a negative 2.5 centimeters? Somebody say, uh-huh. I didn't hear any uh-huhs.
Yes, sir.
Yeah, there you go. Okay, well, let me show you where that is. That's 7.5 over and 2.5 down. You know what? That puts it right there. See this distance here is 2.5. And this distance here is 7.5. And boy, Jove, do you notice that this is exactly halfway between a line going between those two bodies? Since they have the same mass, does it stand to reason that the center of gravity of the whole thing is right there? There, we just did a centroid of length. And if we could spend the rest of our time together doing centroids of center of gravity, center of volume, so forth. That's enough of that. I'm going to move on to more exciting things unless you have a question. But now you've had a lesson on center of gravity, centroids of area, centroids of volume. They all have the same kind of formula. I hope I didn't confuse anybody. Any comments or questions before we move on? All right, now our main topic here is Newton's second law. And I want to do a problem here and show you how these are supposed to be done. Let me make some room here. I'm going to erase this unless somebody speaks up. Here's your chance. Going once. Going twice. Going. All right. Now, Newton's second law. There's our old familiar Newton's second law that goes like this. I'm not happy with that one. Let me find a different one. Now that one is for Newton's second law for translation. And then there's the Newton's second law for rotation. Here, I tell you what, let me do. Let me kind of scoot these over. And I'll scoot this one over. Because I want you guys to make two free body diagrams for me. I've told you this before, but let me tell you again. We're going to do problem 1779, and we're going to make one free body diagram with all the actual forces on it. Find it here. 1779. Yeah, here we go. Make two free body diagrams. Let me draw this one. This is, now they said A has got a mass of 5 kilograms. I'm going to make it come down here a little lower. There's A, and here's B. Now B is big. B is 10 kilograms, and A is 5 kilograms. All right, now there's our diagram. Now we're going to make another diagram for the right side of Newton's second law. Make two diagrams. That's what I want you to do. That one's bigger. B is 10 kilograms. Now, they gave us some information here. We got the 5 kilograms and the 10 kilograms. And this pulley is 3 kilograms. And it has a radius of 0.15 meters. Okay. They said it can be treated as a disc. Well, the moment of inertia for a disc goes like this. Now, you'll find that in the flap of your book, the back flap. The back flap of my book has a disc, and it says 1/2 mr squared. That formula is in the back flap of your book. We could derive that from scratch if you wanted to, but I don't know, we might have. I can't remember if we derived that. I don't think we did, but you could do that. Remember the definition of moment of inertia. Mass moment of inertia is r squared dm. So you could derive that for a disk, but we're not going to do it right now. Okay, now what we're going to do is we're going to put on this left-hand diagram the actual forces. So let me write that. We're going to put the actual forces. And see, on this right-hand diagram, we're going to put the kinetic forces. Okay, let me get my red pencil out here. And we have a force here and a bigger one here. You could draw that a little longer. I could do that one in my head. That one will be 98.1 newtons. But now this one here, I can't do that in my head. Just a minute here. Let's see. It'd be half of the 98.1. 49. This is 4905. Put your forces in red. Now you also have a force going up. There you go. I don't know what to call it. How about just F? Let's just call it F. How's that? Well, that's it, guys. That's all the forces acting on your pulley system. Now over here, what we're going to have is MAs. This is called a kinetic force. And see, this here is going to have an MA going down. It'll actually be an MBA going down. But now this one's not going down. They can't both go down. But this one's going up. I think this one's going to have a longer MA, and this one will have a shorter MA. It's because this is M little a. Now the A's are the same. Whatever the magnitude of the acceleration is, it's the same. These are called kinetic forces. Those are kinetic forces. Okay, great. Now this one, you're going to have to include the kinetic moment. Now, in this case, the kinetic moment's going clockwise. There's your kinetic moment, it's clockwise. There's your kinetic forces. Here's all your forces. There are no couples acting, just forces. And now we're done. We've done our two free body diagrams, and we're ready to write equations. Do you have any questions so far? Now, I'm not sure the book really emphasizes this business of drawing two free body diagrams. I'm trying to look and see here. Yeah, they do. Yeah, they do. They do that. They have the two, but it's sort of subtle. I don't think they spell it out like this. I want two free body diagrams. One is the actual diagram, and one is the kinetic diagram. These are called actual forces. These are called kinetic forces. There are no actual couples acting on this. However, there are moments, but there's no external moment acting on it. And this is called a kinetic moment. Well, let me ask you guys, I need to involve you and see if you guys are listening to me. See if anybody's paying attention here. You see that force right there? We know it has to be holding that pulley up. And there's three possibilities. That force could equal the sum of these two, which is, well, let me just add those. Let me see, 98.1 plus 49.05. I'm getting 147.15. Now, that force is either equal to those, or that force is less than those, or that force is greater than those. Do you understand where I got the 140? Here, I'll show you. I took the 98.1 and the 49.05, and I added them, and I got 147.15. Now, one of these exists. You got a 33 1/3% chance of getting this right. Now, let me go to one of my excellent students here. Alex, unmute and say hello, Alex. Earth calling Alex. Come in, Alex. Well, I can count on Ashley. She was the first one to come on board this morning. Ashley, say hello, please.
Hello.
Hey, Ashley, you got a 33 1/3% chance of getting this right. That's pretty good odds. Is that force there holding up this pulley equal to 147, less than or bigger than 147.15? What do you think, Ashley?
Is it equal?
Ashley's going to go equal. I'm going to put a tick mark there. Well, let me go to one of my other excellent students here. How about my friend Braxton? Braxton, unmute and say hello, Braxton.
Hello.
Yeah, Braxton, vote. I want you voting now. Which one is it? Will that force there holding this pulley up be equal, less than, or greater than 147.15? What do you think, Braxton?
I'm gonna say equal. It's probably wrong, but I'm gonna say equal.
Braxton goes with equal. All right. Well, let's see somebody else here. Mark, unmute and say hello, Mark.
Hello.
Mark, I want you to tell me which one of these three you think is true.
Well, I don't know how much of. Well, the thing is, both of the weights are pulling down on the pulley, and there are
Right.
accelerations on them, but one is accelerating upwards and one is accelerating downwards. So the pulley
Yep.
would feel more of one and less of the other, but
Yeah.
probably by an equal amount, maybe. So, and the rotation of the pulley, the tension wouldn't feel that because the rope goes to the center of the pulley. So I would say equal, maybe.
We we have 3 volts, not volts. This isn't electricity. We have 3 volts that that force is equal to those two, and nobody voted for the others. Well, if we had more time, it would be fun to get the entire class in on this, but we don't have more time. So let's just go ahead and work the problem. But all 3 of you guys are wrong. It's not going to equal that, and we'll try to show you why. The answer lies in these equations right here. These equations are called Newton's second law. So let's write it. Okay, here we go. Let's write it. Let's see. Well, if you write this one, I just need some room. My problem is room, guys. My problem is room. I don't have enough room. But if you write the sum of the forces equation, what you'll have is F is going up. We'll say up is plus. That's the traditional direction. We have F is going up. We have minus 98.1 and minus 49.05. And on the right-hand side, see, I had to erase it, but on the right-hand side, we have the acceleration. But see, the acceleration is we have 5 kilograms times the acceleration. But see, that's negative because it's going down. And then we have 10 kilograms times the acceleration. And that's positive because it's going up. And so what we wind up with is 5 times A. And so what you get, let's see, did I do that right? Let me see. No, I got this wrong. This is the plus, because see, it's going to go up. And this is the minus. I got those backwards. So it's going to go down. And so when you solve this, you get an acceleration of, well, we don't know. We don't know because we don't know what that F is. Do we? We have 2 unknowns, so we can't solve it. However, we're not done yet. We've got another equation. We got this one. Let's do this one then. There we go. I hate to erase it, but we'll see it again, trust me. Now on this one, we have the sum of the moments. We'll take the sum of the moments about this point A here. Let's call it A. That's good. And what we have is, well, that force doesn't give you a moment, but this one does. Let me write my moments. This is not traditional. I'm going to write them as clockwise because that's the way it's going. We got 98.1 times 0.15 meters. That's clockwise, and so I'm writing it plus, minus the 49.05. That's supposed to be a minus, times the 0.15. And that's it, guys. There are no other moments because that doesn't give you a moment. And that's going to equal the moment of inertia. Did we ever get the moment of inertia? I forget. You know, the equation goes like this: 1/2 m r squared. Let's get that. I forget, did we do that? It's 1/2. I don't think we did it. It's 1/2 times 3 times 0.15 squared. Maybe I should write that out. It's 1/2 times 3 times 0.15 squared. Now what I got is 0.03375. Uh-oh, I ran out of room. Kilogram meter squared. So on the right here, we have 0.03375 kilogram meter squared times the alpha. Isn't that how it goes? See, I had to erase it, but isn't that how it goes? The sum of the moments is equal to I alpha. Well, we can solve for alpha. Let's do it. I'm going to shut up now and give you guys 1 minute. And I want you to solve for alpha. And then I'll call on one of my students and we'll get our angular acceleration. On your mark, get set, go. I must have done something wrong. I'm getting a crazy answer. Well, no, maybe it's good. Maybe it's good. No, I think it's something is terribly wrong here. Oh, oh. This is wrong. Now that is correct for the pulley, but but I'm missing the two. Here, let me write this for you. I need the room here. Guys, never mind what this is what I have is wrong. I'm missing some stuff. The way it works is the sum of the moments about A is equal to, in this case, the sum of the kinetic moments about A. And the kinetic moments include the moments caused by these MAs. And see, that's going to equal not only the I alpha, but the R cross MAs. There's two of them. These little guys here are called kinetic moments, and you can't just forget about them. All I've got here is the kinetic moment for the pulley, but see, there's kinetic moments associated with these bodies here. And now we're going to find our answer. Now, what I had here was correct so far, but I'm missing two terms. So let me put those two terms in, and then I'll turn you guys loose to do to push your buttons on your calculators. See, what I'm missing here is the R cross MA. Well, the R is 0.15, and the mass of A is 5. And the acceleration of A is alpha times 0.15. And then you have to add to it the kinetic moment of B, which is the R, which is 0.15, times 10 kilograms times alpha times 0.15. Do you remember that A is equal to R alpha? Translational acceleration is equal to R times angular acceleration. That's what I'm doing here. I've got R times your angular acceleration. Can you read my writing? That's supposed to be an alpha. There we go. Okay, now we've got a correct equation, and what I had was wrong, but I've corrected it now. Now I want you to plug that in, and I want you to solve. I want you to solve for the angular acceleration. Go for it. Okay, I've got my angular acceleration. Let's go to one of my students here. And Braxton, do you have that angular acceleration yet?
Yeah, I got 19.818.
That's what I got. What are the units on angular acceleration, Braxton?
Radians per second squared.
You got it. Jolly good show. It's nothings per second squared. Remember, radians are dimensionless. Hey, well, now we can get the translational acceleration. It's just equal to r times alpha. And r is 0.15. So multiply that times 0.15, and you'll get 2.97, I don't know, 3 meters per second squared. See, this is accelerating downward with that kind of acceleration, and this is accelerating upward with the same acceleration. Great. And we understand all that, I hope. Now, what were we supposed to find in this problem anyway? Let me read it here. Determine, oh, that's what we're supposed to find. We'll look in the back and see what it says for 1779. We'll see what the answer book says. 1779. They said acceleration is 2.97. The book says 2.97 meters per second squared. You know what? They just kind of rounded off, didn't they? We did great. But I want to talk to you about this just a little bit more. See, this is using something called kinetic moments. You might not be quite comfortable with those yet. I want to show you another way of doing this. But first, let's find the tensions in here. In fact, let's just do it the other way first, and that we'll get the tensions that way. We're going to do this problem a different way now. Do you realize what we did was we looked at the whole system and we wrote the sum of the moments on the whole system and the sum of the kinetic moments on the whole system. And before that, I had to erase it, but we wrote the forces on the whole system and the kinetic forces on the whole system. But now what we're going to do is we're going to break the system into parts. You've done that before. You've broken things into parts. And we're going to write the equations in parts. So I just need the room here. Let me erase all this. We've got our answers. We have our acceleration. We got everything we need here. And what we're going to do is break this into parts. And we're just going to look at body A. Well, see, body A has a tension on it, and that tension actually is bigger. It's got a bigger tension than 4905 because it's going to go zooming up. You know that. It's got to be bigger because it's going to go up. This one's going to go down. So the tension on it will be the same as the tension on A, but it's smaller than 98.1. Here, I'll make that obviously bigger. These tensions are the same, but the tension's less than 98.1, but it's bigger than 4905. And we can get that by using Newton's second law for translation. So let's write the Newton's second law for translation just for body A. Here we go. Well, for body A, we've got tension going up minus 4905 going down equals the mass 5 kilograms ton acceleration, which we've already done that. We know the acceleration is 2.973. meters per second squared. So we can solve for the tension. Go ahead and solve that for the tension with me. And I'm going to do it. I got a tension of 63.91 newtons. Well, that has to be the same tension on that body there. Let's write the sum of forces on body B. Here we go. That was the sum of forces on body A. On body B, we have, well, now it's going down, right? Yeah, so I'm going to write that as 98.1 newtons minus my tension, which we think is 63.91, equals that mass times the acceleration of body B, which is the same as body A. Now solve that and see what we get. We better get the 2.973. Try it and see if it works. Well, it didn't work. Something bad happened. Let me see what happened here. Let's see. We got 98.1 minus the tension equals the 10 times acceleration. Must have done something wrong. I wonder what I did wrong. I got this right. Let me go back over this. Tension minus that equals 5 times the acceleration, which is, we think, is 2.973. Okay. Let me do that again. I might have pushed the wrong button or something here. No, I'm getting this. And on this one here, we got 98.1 minus the tension equals 10 times acceleration of B. Well, I'm getting acceleration of B I'm getting a different answer here. I've done something horribly wrong. However, we got this answer in the back of the book. We think we're right about that. Oh, I'm wrong. These tensions are not the same. You know what I'm thinking of, guys? I'm thinking back in the old days when we had pulleys that were massless. Well, this pulley is not massless. It's got a mass of 3 kilograms. These tensions are not the same. We're going to call this tension 1 and tension 2. And so here's where I made my mistake. Actually, I think you guys learn more from my mistakes than you do otherwise. This is correct. The tension in 1 is 63.91. We did good on that. Now we're going to do the tension in on 2 there. That will be a 98.1 minus the tension on 2 equals 10 kilograms times you 2.973 meters per second squared. Now we're going to solve for the tension on 2. Here we go. All right. Times 10. And then you have to subtract 98.1. I'm getting the tension on 2 is 68.37 newtons. You know what? This tension here, I told you before, and I was wrong. I was saying that these tensions are the same. They're not. This tension's bigger. Not much, but it is bigger. It's 68 something newtons, and this tension here is 63 something newtons. Well, it makes sense. Now let's check our work. We're going to check our work by just looking at the pulley itself. We're just looking at the pulley itself. Now it's got a force pulling up. And we'll discuss that in a little while, because we had several students that thought that force was going to equal the sum of these two. But see, it's got a tension pulling down here of 68.37 and a tension pulling down here, it's a little smaller, 63.91. And now really this is a check of our work. We've got all our answers. But if you take the sum of the moments just on this pulley, you know how that goes. The sum of the moments on the pulley equals the moment of inertia times the alpha. All right, so you're going to have the 68.37 times the 0.15 meters minus the 63.91 times 0.15 meters equals, what did we say the I was? I forgot. We did it. I think I erased it. Well, I can find it. It's 1/2 times times 3 times 0.15 squared. There it is. It's equal to the Ig, which is 0.03375 kilogram meter squared times alpha. Now we can solve this equation here, and we can get our angular acceleration, and it darn well better be 19.818. If it is, then we've done everything right. Plug all that into your calculators and tell me what you get. All right, well, here goes. I'm getting 19.82, which is rounded off the same as our alpha. So check. We've got everything correct. We have our alpha, we have our A, we have our tensions, only they're different. And what I told you before, that they're the same. See, they would be the same if this was a massless, frictionless pulley, but it's not. Now, getting back to my original question for you guys. My original question was, I forgot what it was now. Oh, it was this force here. can you guys see, because this pulley's not going anyplace, that the sum of the forces is going to be 0 on just the pulley alone? Because it doesn't have linear acceleration now. It's got angular acceleration, but Newton's second law, translationally, sum of the forces is 0. So that force is equal to, well, whatever those are when you add them up. What's 6391? 6391 plus 6837. It's 132 rounded off to 3 newtons. And remember, when you add these up, the 4905, I erased it, plus the 98.1, that's 147. So this force is less than, does that show up? Yeah, this force is less than the 147.15. Remember our 3 choices? We had 4, I think it was 4 students that thought that that force would equal these 2 forces. Well, it's not, it's less than. It's less than because the sum of the forces is equal to MA, where this is be the center of mass. Well, what's the center of mass of this system? Well, it's not here. The center of mass of that system, that's the center of mass of the pulley. But right at this instant, the center of mass would be, I don't know, over here someplace. It's closer to the 10 than the 5. And it's not even there because if you consider the whole system, I don't know, it's in here someplace. But regardless of where it is exactly, it's going down because the sum of the forces is going down, isn't it? Don't these 2 add up to 132, which is less than 147? So that there's more force going down than up. And so if the sum of the forces is down, the sum of the acceleration for the center of mass is down. I don't know if that made a lick of sense to anybody, but we had fun doing it, and I hope you learned something. And you learned you learned about these kinetic moments in drawing 2 diagrams. Let's just do another problem, and we'll draw two diagrams. But first, are there any questions on that? Well, okay, we're going to erase that and do another problem. Here goes. Okay, now this one here is problem 1758. And I'm going to draw 2 free body diagrams. That's what I want you guys to do on your problems. Now this one's a square. So I'm going to try to draw a square. That's pretty good. I'm going to draw another square. Okay. There's another square. There we go. That's there. That square is smaller than the other one. Let me make it a little bigger. A little bit bigger, maybe, not much. Well, I tried to draw 2 squares. Now these are 0.5 meters by 0.5 meters. 0.5 meters, 0.5 meters, yeah. And now you realize what we're doing. We have the sum of the forces equals ma. That's Newton's second law for translation. And so we'll put all of the forces in red on this diagram here. And we'll put the kinetic forces. These are called kinetic forces. We'll put them on this diagram here. Okay, and this is a 24 kilogram plate. So let me write that down someplace, 24 kilograms. It's released from rest. They want the angular acceleration and the reactions at point. Okay, so we'll do that. Right now, we're talking about Newton's second law. And for translation, it goes like this. There's a left-hand side of Newton's second law, and there's a right-hand side of Newton's second law. And what we're going to do is we're going to draw a free body diagram for the left-hand side of Newton's second law, and then another free body diagram called the kinetic diagram for the right-hand side of Newton's second law. Okay. Great. Well, let's get the red pencil out. Won't there be a weight going down right here of I don't know, what's 24 times 9.81? Hang on a minute. 24 times 9.81. 235.44. Guys, if I mess up, you speak up and help me here, but I get 235.44 newtons there. But now I predict there's going to be a force going up here. And there could be a force going left or right here. I wonder if it'll be going to the right or to the left. Let me ask somebody here. Let me go to one of my excellent students. Alex, unmute and say hello, Alex. He's not going to answer me. He's busy. Coffee break. Stuart, unmute and say hello, Stuart.
Hello.
Hey, Stuart, I'm trying to decide, do I want to draw my force acting there going to the left or to the right? What do you think?
I'd say to the left.
You know what, Stuart? I do too. I think it's going to the left. It's just a gut feeling. But I think we're both right. But I think we're done now. We've done all the red stuff on that. Now let's do the red stuff on the kinetic diagram. See, there's also an equation that goes like this. What's that symbol there? I can't figure out what I wrote there. There's another equation that goes like this. Put the equal sign kind of in the middle there. And the way the book writes this, they write this as the sum of the kinetic moments. Oh, I know it. That was a vector sign. That's what it was. They call them kinetic moments. Okay. And in this case here, that's just going to be IG alpha. There are no R cross MAs. Well, now, wait a minute. No, I don't think there are. I don't think there's any R cross MAs. I think it's just like that. Let's get this IG thing. There's an equation for that. It's in the flap of your book. By the way, this thing's gonna rotate clockwise. So the IG alpha is going clockwise, but there is an MA. I haven't done the MAG yet. See, here's G right here. That's G. Now, when you turn this thing loose, if it's got a pin right here, the direction of that MAG is not straight down. This thing's going to kind of swing around in a circle. See, it's going to swing around. Can you see that? It's going to swing, and the MAG is going to be going like that. There you go. There's your MAG. There's your MAG. There's your, see, that's your kinetic force, and that's your kinetic moment. These are your actual forces. We have that one, but we don't have these. Let's give them names. How about, I don't know, AY would be a nice name for that one. And AX, we can have X go over to the left if you want. We can have it do any way you want. This is our problem. So there's our two diagrams. Now let's get this IG thing. There's an equation for that in the flap of your book. It's 1/12 the mass times, in this case, it'd be 0.5 squared plus 0.5 squared. And get your book and turn, go to the flap, back here in the back, and there's a plate there. See that plate where my thumb is wiggling? That's the equation for it. It's 1/12 m times a squared plus b squared. There it is. Okay. Well, what's m? Well, that's the 24 kilograms. So put in the 24 kilograms. And put that in there, and I'm going to put it in there. We're going to find our, this has got a name. It's called the mass moment of inertia is the fancy name for it. It's called the mass moment of inertia. And we're going to have it. Here goes. Gee, I got a weird answer. I just got 1. Did you get 1? I got 1 kilogram meter squared. Ta-da, and we got that. Okay. Well, good. Well, let's write our equations now. Why don't we write this one? This is your Newton's second law for translation. Do I have room over here? I think so. Now I decided that the x-axis is going this way. We can do that. We can pick it that way. And so that's the only force we have in the x direction. So the sum of the forces in the x direction, what I'm doing right now is I'm writing Newton's second law in that x direction going to the left. So what I have there is AX equals the mass times MAGX. Well, this is MAG. If you want the x component, I think that's 45 degrees. Can you tell? I mean, it's a square, And if you go from corner to corner, yeah, it's 45 degrees. So you know what that is 24 kilograms times AG cosine of 45. So we have a nice equation in the x direction. Now let's do the y direction. The sum of the forces in the y direction will equal MAG in the y direction. Now I picked y going up, so that's fine. So let's write that. We have AY going up minus 235, 44 equals, well, this would be MAG sine of 45. So far we have two lovely equations, but we don't know AX, and we don't know AG, and we don't know AY, and we don't know AG. But we're not done yet. We still got this one. Let's write this one. And need some room here. See, we figured out IG is 1 kilogram meter squared. I need this room, so let me make some room, and we're going to write this. We're going to write this equation here now. Here goes. Sum of the moments about G. Well, you know what? Both of those moments go clockwise, you know? No. This one's counterclockwise. That one's clockwise. Here's what you got. You know this is going to be clockwise. So I'm going to write everything clockwise. We got AX times this distance here, which is 0.25. See, from G up to the line of sight of AX is 0.25. And that gives you a, wait a minute, no, that's counterclockwise. Let's do it this way. You've got AY times 0.25 meters clockwise minus AX times 0.25 meters. Now that's counterclockwise, and that's it, equals 1 kilogram meter squared times alpha. Well, let's see what we got here. I'm going to box up these equations. We got some lovely equations. We have one for AX, one for AY, and then we have this one here. Let's count our unknowns. Let's see, we have AX, we don't know what it is. AY, we don't know what that is. AG, we don't know what that is. And alpha, uh-oh, 3 equations and 4 unknowns. We need another equation. There is another equation. Does anybody out there in this pile of wonderful students that I have? We got Stuart, Shane, Mark, Braxton, Ashley, Alex. We got all these wonderful students. We need another equation. What's the other equation that we need? Does anybody out there know?
Acceleration equals R alpha.
That's it. There's an equation that goes like this. AG equals R alpha. But see, what we need is this R here, because we're rotating about this pivot. And I'm going to have to think about what that R is. It's 0.5 cosine of 45 is what it is. 0.5 cosine 45 equals, it's 0.35355 alpha. There's our other equation. So now what do we do with it? We got some ugly algebra to do, don't we? But we got enough equations. We've got enough equations, we can solve it. It's just that I'm scared of the algebra right now, and we only have 3 minutes left. And I want to show you an easier way. This is called a fixed pivot. Everything I've told you is okay. All these equations are good. But when you have a fixed pivot, you can write this equation here. Call that point A. If it's a fixed pivot, you can write that equation there, which I'll have to talk to you more about on Wednesday. But see, we can get IA, that's not a problem. IA is just equal to IG plus MD squared between the distance between A and G. They got a name for this equation. It's called the parallel axis theorem. Now we know IG, it's 1. The mass is 24 kilograms, and that distance we just figured out is 0.35355, but you have to square it now. And so IA is equal to, hang on, we're running out of time, but I think we got time to get this whipped here. 0.35 blah, blah, blah squared times 24 plus 1. Gee, I get 4. Isn't that weird? I get 4. So the moments about A is equal to the 235/44 times your 0.25 meters, because that's how far over you got to go to the line of sight or line of action. And that's equal to 4 alpha. Isn't that nice? Look at that equation there. Isn't that pretty? So you can get your alpha real easy. Here goes. Alpha is I got my alpha. Alpha is equal to 14.715. And from that, you can get your acceleration. It's just going to be that alpha times that. Which is 5.2 meters per second squared. So we got alpha, we got A, and with that knowledge, we can get AX and AY. Now, what were we supposed to find out? Let me read this. Let's see what it says here. Oh, I'm out of time. Oh, it's so sad. Determine the angular acceleration. Well, let's look at the answer book and see if we got this alpha right. Go to the back and look up 1758. 1758. Alpha says 14.7 in the back. The book says alpha is 14.7. They rounded off. We did great. Go do your homework. Plug that in and get your values for AX and AY. It's sad, but we're out of time. Any last comments or questions before I terminate? I'm the Terminator. We're going to terminate our session, but here's your chance to speak up. Okay, well, we had fun, and I need to talk to you more about this fixed pivot equation on Thursday. Okay, nobody said anything. Goodbye, students, for now. See you Wednesday at 9:30. Bye-bye.
Bye.
Bye. Bye-bye, everybody. Be careful.